Okay, so now I'll start. So today, I want to give a review of section 13.1 and 13.2 because there are a lot of new people. So basically, I think the review will last the first 30 minutes, I expect, and then the final 30 minutes I'll just do section 13.4. Well, half of section 13.4. Okay, so I'm just gonna review section 13.1 and 13.2. So 13.1 is basic theory of field extensions. So, all right. So you have a field F, and what this means is a commutative ring with an identity element, and every non-zero element is a unit. And then the characteristic of F is the smallest integer p, such that p times 1 equals 0 if p exists and 0 otherwise. Then we use this notation k over f to denote an extension, i.e. a field k containing f. So we also use like this type of notation, k over f. It still means an extension. So k is a field that contains f. And then this notation means the degree of the extension. So this is the dimension of k as a vector space over f. To denote this, we also do this type of thing. So k over f with an n. So this is the degree of k over f, the dimension of k as a vector space over f. Okay, so here's a proposition. So f is a homomorphism of fields. Then phi is a homomorphism of fields. That means phi is either the zero map or phi is an injection. Let's see. Phi is either the zero map or phi is an injection. So a theorem: if f is a field and p is an irreducible polynomial with coefficients in this field, there exists a field k containing an isomorphic copy of f in which p has a root. Okay. A bunch of new people have joined. So let me just repeat. So you have a field f, which is a commutative ring with an identity element, and every non-zero element is a unit. The characteristic of f is the smallest integer p, such that p times 1 equals 0, or it's 0 otherwise. And then this notation is for extensions. So fields containing f, k over f is a field containing f. And we also write it like this: k is a field containing f. Then the degree is the dimension of k as a vector space over f, and we also write like this: k n f. So the degree of k over f is n. And then this proposition is an important proposition about fields, right? Whenever you have a homomorphism of fields, either it's the zero map or it's an injection, right? Why is this? Because since fields, every non-zero element is a unit, that means the only ideals of a field are either the zero ideal or the full field, right? So the kernel of this map can either be the zero ideal or the whole field. So either the kernel is 0, in which case it's an injection, or it's the whole field, in which case everything goes to 0. So the map is 0. So that's an important property about fields. Homomorphisms are either 0 identically or an injection. And then, okay, so here's the first real theorem. So you have a field f, you have a polynomial p, which is irreducible with coefficients in f. The conclusion of the theorem is that there exists a field k containing an isomorphic copy of f in which p has a root. So the way you prove this is by you construct this quotient field, right? So this is a field because p is a maximal ideal, because p is an irreducible polynomial. So irreducible, p of x is irreducible if and only if this ideal is maximal, if and only if when you quotient out by a maximal ideal you get a field. So this is a field, and in this field p of x has a root, right? Just let you know you're quotienting out by p of x, so p of x is basically 0 in this field. So the element x in this field is a root of P of X. Are there any questions so far? I'm just giving a review of the first two sections. Okay, now F adjoin alpha adjoin beta dot dot dot. This is notation for the smallest subfield of K containing F, alpha, beta dot dot dot. F adjoin alpha, this is a simple extension, and alpha is called the primitive element of this extension. So here's a theorem. If F is a field and P is an irreducible polynomial in F with coefficients in F, and alpha is a root of P of X, then F adjoin alpha is isomorphic to the polynomial ring F adjoin X mod this irreducible polynomial P of X. And the way you prove this is by having this natural homomorphism from f of x to f of alpha, sending f to alpha. And then the kernel of this map will be P of x, the ideal generated by P of x, and then the first isomorphism theorem gives you that f of x mod P of x is f of alpha. Right. Okay. Now, okay, so this is another isomorphism theorem. So you have f, you have phi is an isomorphism between two fields, f and f prime, and P of x is an irreducible polynomial with coefficients in f. P prime of x is obtained by applying phi to the coefficients of P of x. Alpha is a root of P of x, and beta is a root of P prime of x. You conclude that f of alpha is isomorphic to f of beta, f adjoin beta. And this isomorphism extends phi by taking alpha to beta. And the way you prove this is by using the previous fact that we proved, that a simple extension is just the ring of polynomials modulo this irreducible polynomial. So that's f of alpha is isomorphic to f adjoin x mod P of x. And then this is isomorphic to f adjoin f prime adjoin x mod P prime of x. This is the so here you take f adjoin x to f prime adjoin x with this map phi, and then that takes this maximal ideal P of x to this maximal ideal P prime of x. And then here you have the isomorphism again to f adjoin beta. Alright. So here's the picture of what's going on. You have f is isomorphic to f prime via the map phi, and then you can extend this map to an isomorphism of f adjoin alpha, to where alpha is a root of this irreducible polynomial, and beta is a root of the image of this irreducible polynomial by the isomorphism phi. All right. Okay, so that was basically a summary of 13.1. Are there any questions about what's happening? Okay. Let me see. All right. Okay, so 13.2 is about algebraic extensions. Yeah. So, okay, so a definition, alpha is algebraic over f. So alpha belongs to this extension field K if alpha is a root of some non-zero polynomial f of x. Yeah. So proposition, alpha is algebraic over f if there So suppose you have an algebraic element over f then there exists a unique monic irreducible polynomial with alpha as a root. So we already know about the existence of some polynomial with alpha as a root. That's what algebraic means. But now we know that there exists a unique monic irreducible polynomial. And the way you prove this is by so you have g, which is a polynomial. You let it be a polynomial of minimal degree, and then you show that it's irreducible, and then you prove it's unique with Euclidean division of polynomials. So the polynomial, this polynomial, the unique irreducible monic polynomial with alpha as a root, is called the minimal polynomial of alpha over f. And then we know that the simple extension f adjoin this algebraic element over f is isomorphic to f, the polynomial ring fx modulo this maximal ideal generated by the minimal polynomial of alpha. So the degree of f alpha over f is the degree of the minimal polynomial of alpha. And a basis for this simple extension is 1 alpha alpha squared dot 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 alpha to the n minus 1, where n is the degree of the minimal polynomial. Okay, so now we're gonna prove so here we go. We have alpha is algebraic over f if and only if f of alpha over f is a finite extension. So I call this one of the most important proofs because it has a really simple idea that's like I find it really important, right? So so the forwards direction is alpha is algebraic implies that this degree is finite. That's just the previous proposition, right? Alpha is algebraic gives you this finite degree. So yeah, if you have alpha algebraic over f, then this is a finite extension. But the backwards direction is where you have the important idea. So say this is a finite extension, so it's a finite dimensional vector space over f. So and it has dimension n. N, let's say. So let's take these elements 1 alpha alpha squared alpha to the n. These are n plus 1 elements, so they have to be linearly dependent over f, right? So there has to be some linear combination of field elements b not with coefficients in f not all zero, such that you get the linear combination is 0. So this is what linear dependence means. So then this tells you that alpha is a root of this polynomial that you just got from linear dependence, right? So alpha is a root of this polynomial, and that means alpha is algebraic over f. So that's how the simple extension being finite implies that the element you adjoined is algebraic, right? So that's really important. That's a really important idea. And then an important corollary is that k over f being a finite extension, again this means the dimension of k over f is finite, implies that k over f is an algebraic extension. And what this means is that every element of k is algebraic over f. So the way you prove this is just doing, so we want to prove every element of k is algebraic over f. Pick any element of k, and we're going to try to prove it's algebraic over f. So look at the simple extension f adjoin alpha. This is a subspace of k. Because k contains alpha, it has to contain the smallest field containing alpha. And this is f adjoin alpha. So this is a subspace, and that means the vector space dimension is smaller than the total dimension. So f of alpha over f has a dimension smaller than k over f. Right? And k over f is finite by the hypothesis, so that means f of alpha over f is also finite. So this is a finite extension, and then since the simple extension is finite, that means that the element you joined is algebraic. That's the content of this forwards direction. This being finite means this is algebraic, right? So that's how we prove that an extension being finite means that extension is algebraic. All right. Now here's another important theorem. Say you have a tower of extensions. F is contained in K is contained in L. Then the degree of L over K is the degree of L over the degree of L over F is the degree of L over K times the degree of K over F. Right. So yeah, how do you prove this? Well, okay, so my proof is only going to be about finite extensions. So let's start with a basis of K over F. So this vector space has this basis. And let's have a basis Bj, a basis of L over K. So this vector space has this basis. And then you want to prove that alpha I beta j is a basis for L over F. So the basis of this vector space, L over F. So if this had this degree, that many elements, and this had that many elements, then this basis has the product many elements. So that shows you that the degree is multiplicative in towers. Right. And then an important corollary is that if you have a tower of extensions, then the degree of K over F divides the degree of L over F. Okay, so that's basically all I wanted to say about section 13.1 and 13.2. Well, there's some more stuff in 13.2, but I didn't get to that. Are there any questions? Okay. All right. Now I'll do I'll start 13.4, but I'll finish this on Friday. So the goal of the rest of the lecture today is to define the splitting field and to see two examples. We're gonna see two examples. One of them being the cyclotomic field, and the other one being the splitting field of x to the p minus 2. Right. Okay, so let's define the splitting field. So let f be a field and f be a polynomial with coefficients in f. Recall there exists an extension of f in which f of x has a root. Right? So there exists an extension k of f such that there exists an element of k which is a root of f. F of alpha is equal to 0. Right? So this means that x minus alpha is a linear factor of f of x in the polynomial ring with coefficients in k. Right? So yeah. Now, what does it mean to be a splitting field? K over f, this extension is a splitting field for the polynomial f of x with coefficients in f if f of x factors completely into linear factors in the ring of polynomials with coefficients in k. So we say that f of x splits completely. So and furthermore, k contains no smaller subfields which have this property. So a splitting field is a field extension of f in which this polynomial f of x splits completely. Right. So note that the degree of f is n, and so that means f of x has at most n roots in f. And so f of x has precisely n roots if and only if f of x splits completely. Right. All right. So here's the first theorem in the section. So for a field f, if f of x is a polynomial with coefficients in f, there exists an extension k of f, which is a splitting field for f of x. So this theorem is just telling you for any polynomial with coefficients in f, there exists a splitting field for that polynomial. So how are we going to prove the existence of the splitting field? Well, we'll do it by induction. So let n be the degree of f, and the base case is n equals 1. So suppose n equals 1, it means the degree of f is 1, so f is linear. And this means that the only root of f is already in the base field f. So we didn't have to construct any extension field. E already has all of the roots. So yeah, f of x is linear, so it splits completely already, right? So the base case is just immediate, right? So the induction step, suppose that the result holds for all polynomials of degree n minus 1. So suppose for all polynomials of degree n minus 1, there exists a splitting field, right? So say f of x has irreducible factor n, and call it p of x. There exists an extension of f, call it e1, in which p of x has a root, call it alpha. Right. So I'm taking an irreducible factor of f of x and finding a root of this polynomial of this irreducible factor, and this root belongs in an extension e1. Then in e1 of x, p of x has x minus alpha as a linear factor, and the degree of the remaining factor is f1. The degree of the remaining factor f1 of x is n minus 1. So, alright, so you have a polynomial f of x, and then you look at an irreducible factor, p of x, of degree n. Find a root of it in some extension. We already know that you can find an extension of your base field which contains a root of an irreducible polynomial. So we do this, and that gives you the field e1, and then in this field you get alpha. So in over this field, the original polynomial f factors as x minus alpha times some degree n minus 1 polynomial f1 of x, right? But then by the inductive hypothesis, there exists an extension e1 of an extension e of e1 over which f1 splits completely. Since f1 is degree n minus 1, and induction assumption was that all polynomials of degree n minus 1 there exist extensions in which they split completely, we get this extension, e of e1. And then alpha is already in e, because alpha is in e1, so and e is an extension of e1. So alpha is in e, so e contains all the roots of f of x. So we've shown by induction the existence of a field which contains all of the roots of f. Right. Now take K as the intersection of all subfields of E containing f and all of the roots of f of x. Right. Then K is a splitting field of f of x. So this shows so basically, how do you prove that if you have a field and a polynomial in that field that there exists a splitting field of that polynomial? Well, you do it by induction, right? Cool. Okay, here's just a terminology. Like, if you have K is an algebraic extension of f, which is a splitting field over f for a collection of polynomials f of x in f, the polynomial ring with coefficients in f, then K is called a normal extension of f. So normal means you're a splitting field of a collection of polynomials. So that's just terminology. And then a splitting field of a polynomial of degree n over f is of degree at most n factorial over f. Okay. So, right. So how are we going to prove this? So we have our polynomial f of degree n, and we want to prove that the degree of the splitting field of f is at most n factorial over f. Alright, so let's adjoin one root alpha of f of x to f, so we get this simple extension f adjoin alpha. Right, its degree is less than the degree of f, because we didn't assume that f was irreducible. So its degree is equal to the degree of this extension is less than or equal to the degree of f, which is n. So write f1 is f adjoin alpha. Over f1, the polynomial f of x has linear factor x minus alpha. right? So any root beta satisfies an equation of degree at most n minus 1 over f1, right? So if you adjoin another root beta that's distinct from alpha, its degree over f1 is going to be at most n minus 1 by the same logic. So first you joined a root of a polynomial of degree n, and now you're adjoining to that extension a root of a polynomial of degree n minus 1. So first, the first extension was at most degree n, and the second extension is at most degree n minus 1. And in this way, you get n factorial, right? So the splitting field, you have to adjoin all of the roots. So you do a tower of extensions by first adjoining one root, then the second, then the third, and then so on. And you can have at most n roots, and each time the degree is decreased by at least 1, right? Because you're pulling out more linear factors, right? So you get you get n times n minus 1 dot 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 all the way down. So the degree of the splitting field of a polynomial of degree n over f is at most n factorial. Okay. I'll just make a side remark here, right? So the degree of the symmetric group, or the order of the symmetric group, is n factorial, right? Hold on. The order of the symmetric group is n factorial. And this is not a coincidence, because when we get to Galois theory, we'll see how field extensions correspond to Galois groups, and it turns out for most polynomials, their Galois groups is the symmetric polynomial. So, yeah. Anyway, that's later. Okay, now let's talk about two examples. Alright, so the first example is a splitting field of x to the n minus 1. And this is the cyclotomic field. Alright, so consider the splitting field of x to the n minus 1 over q. The roots are called the nth roots of unity. And over C, there are n distinct solutions. So there are these things, e to the 2 pi ki over n. So visually, you have 1 e to the 2 pi I over n. And then you have all of its powers, e to the 2 pi e to the 2 pi ki over n, where k ranges from 0 to n minus 1. So you have n distinct solutions. So these are all of the roots of x to the n minus 1. So C contains the splitting field of x to the n minus 1 over q. Right. The roots form a cyclic group of order n generated by e to the 2 pi I over n, right? So if you just take this root and then take powers of it, you'll get all of the other roots, right? So that's why it's a cyclic group. And a generator for the cyclic group of all nth roots of unity is called the primitive nth root of unity. So let zeta n denote a primitive nth root of unity. The other primitive nth roots of unity are zeta n to the a, where a is some integer relatively prime to n. So if you take, let's say, I don't know, let's say n is equal to 15 and a is equal to 7, a is relatively prime to 15, so that gives you that zeta 15 to the a 7 is a primitive root. So if you take powers of that number, you'll generate all of the other roots. So in particular, there are precisely phi of n primitive roots of unity. So phi is the Euler-Tauschent function. It counts how many coprime numbers there are less than n to coprime to n. Right. So the splitting field of x to the n minus 1 over q is the splitting field of q adjoin zeta n. And q adjoin zeta n is called the cyclotomic field of nth roots of unity. Right. Okay. Okay. So that's the cyclotomic field of nth roots of unity. This is the splitting field of x to the n minus 1. All right. So the next question is, what is the degree of the nth cyclotomic field? Right. So in the case that n is a prime, we know the answer. So I'll show you how we know the answer. We have x to the p minus 1. It factors as x minus 1 times this polynomial. X minus 1 is a factor because 1 is a root of this polynomial, and we do long division to get this factor. Right. So this we denote it like this. The pth cyclotomic polynomial is x to the p minus 1 divided by x minus 1. And it's this polynomial, x to the p minus 1 plus x to the p minus 2 plus dot 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 x plus 1. And this is irreducible over Q. The way you see it's irreducible is by using Eisenstein's criteria at on this polynomial, on the shift of this polynomial, phi p x plus 1 at the prime p. So if you do the computation, this is this, you plug in x plus 1, and then you see that all of the terms that are not the leading term have a factor of p, but this guy doesn't have a factor of p. So it's irreducible. Okay. So the degree of the pth cyclotomic extension is the degree of this cyclotomic polynomial, which is p minus 1. So yeah, p minus 1. So we know the degree of the pth cyclotomic field, and then later on we're going to see that the degree of the nth cyclotomic field is phi of n, the Euler-Toshin function, which is the number of primitive roots. Yeah, phi of p is p minus 1. So that checks out right there. And again, I guess I'll note that the group of units mod. Okay. Right. The group of units mod n has order phi of n. Right. So there are n units mod n, and it turns out that the Galois group is this group. So that's just something for the future. But yeah. All right, here's the second example of splitting fields. We have x to the p minus 2, where p is a prime. So let p be a prime and consider the splitting field x to the p minus 2. If alpha is a root, then alpha to the p equals 2, and also zeta alpha to the p equals 2, where zeta is a pth root of unity. Right? If you take zeta to the p, you're just going to get 1. You're a pth root of unity. So zeta alpha to the p is also 2. So these are p distinct roots of the polynomial x to the p minus 2. Right? So the solutions are zeta pth root of 2, where zeta is a pth root of unity. Okay, so the splitting field of this polynomial contains all of these roots, and it's the smallest field containing all of these roots. Right? Notice that the quotient of two of these roots is a pth root of unity. So primitive pth roots of unity are in the splitting field. They're just quotients of two roots. And roots are in the field, so quotients of roots are in the field. So primitive pth roots are in the field. Right? So the splitting field contains the pth root of 2, and it also contains a primitive pth root of unity. So the splitting field contains this field, q adjoin p root of 2 adjoin zeta p, which is a primitive p root. But also all of the roots are in this field, right? So this contains the splitting field. So the splitting field is contained in this field, and this contains the splitting field. So this must be the splitting field. And then finally, in this field, you have two sub-extensions, q adjoin the p root of 2 and q adjoin a primitive p root of unity. And then the p root of 2 has degree p over q. Well, why does it have degree p over q? Well, that's because it's a simple extension, right? And you're adjoining an algebraic element, which is the root of x to the p minus 2. And furthermore, this is an irreducible polynomial. So this is the minimal polynomial of that guy. So the degree of the minimal polynomial is the degree of the extension. Right, so this extension is p, and then this extension is p minus 1. We just showed that the cyclotomic field of prime, the p cyclotomic field has the degree p minus 1. So we get these two subfields, one of degree p and one of degree p minus 1. Okay, now what can this extension, what can this field extension degree be? It has to be p, right? And this one has to be p minus 1, because right. So the degree of the total extension is at most p times p minus 1, and then since these are two, p and p minus 1 are relatively prime, that means this degree has to be p, and then this degree has to be p minus 1. All right. Okay, so that's basically all I wanted to say today. I will finish the rest of section 13.4 on Friday. Okay, was I going too fast? Are there any questions? I'm basically done with what I wanted to present. So if there are any questions, I'm happy to answer.
Yeah, so I mean, for me at least, you're going a little fast with the definitions back there. Can you scroll back up to the?
Which?
It was after the proof that every polynomial has a splitting field.
Oh, okay. This?
Both those definitions, or maybe there's only one.
Okay, so we proved. So every polynomial has a splitting field. We did that by induction, right?
Yeah.
And then this is just a technical term. We say an extension is normal if it's a splitting field for a collection of polynomials.
Okay. So if you have some like set of polynomials.
Yeah.
But so like somehow being normal depends on the set of polynomials, like.
So no, you just have a collection. If there exists a collection of polynomials for which this extension is the splitting field of, then we say that extension is normal. Okay, so I should actually give examples. I didn't give any examples. So
like.
Yeah.
I mean, because like when you say collection of polynomials, like, I'm just thinking like, can it just be a set of two polynomials? Like,
yeah,
is it?
Yeah.
Okay. So like as long as as long as it's an algebraic extension of more than one polynomial.
Do you see why this? Yeah. Do you see why this is not normal? Like q adjoin cube root of 2.
It's not obvious to me at all.
Okay. So. All right. So this is. I probably should have talked about this. Right. So. All right. Okay, so you have cube root of 3, cube root of 2, and this is a root of x cubed minus 2, right? So
yeah.
This is a root of this polynomial. and also that this polynomial is irreducible, right? So this is the minimal polynomial of cube root of 2, right?
Yes.
All right. So this is an irreducible polynomial. But what are the other roots of this guy? Well, in C, you have two more roots. You have omega cube root of 2, and you have omega squared cube root of 2. Right? Omega is a primitive third root of unity.
Yeah.
Right.
Okay.
Yeah. But these guys are not in Q adjoin cube root of 2, right? Because this guy is contained in R, but these guys are not in R. That's one way to see it.
Okay.
Right. So yeah, this
that just
field.
means that it doesn't split over
Yeah.
x cubed minus 2?
Yeah, exactly. This field doesn't contain all of the roots of this minimal polynomial, so it's not a splitting field. Right.
Okay.
And we say normal just to mean like it's a splitting field of a collection of polynomials. In particular, like Q adjoin cube root of 2 is not a normal extension because it's not a splitting field.
Okay. But so like they're like because it seems as though when you say it's a splitting field, you have to specify the polynomial over which it is a splitting field.
Yes.
Right.
Yes.
So you just say was that just sort of implicit when you said that q adjoin cube root of 3 doesn't split over this polynomial?
I said Q adjoin cube root of 2 is not a normal extension. And what that means is that there is no collection of polynomials for which this is a splitting field of. Right?
Yeah, okay. And so, like, how do I know that there isn't some other collection of polynomials? I believe you. I certainly believe you that x cubed minus 3, like, it doesn't work for, right?
Mm-hmm.
But maybe there's some other.
Well, remember, like, that the minimal polynomial is unique, right?
Okay.
So if you have an algebraic element or an algebraic element over a field, right, there is a unique minimal polynomial. And if you deem the extension to be normal, that means you have to have all of the conjugates. You have to have all of the roots of this minimal polynomial. So, right, if you have an algebraic element alpha, then its minimal polynomial is m alpha x. And then the other roots of this guy, these are called the conjugates of alpha, right? So what it means to be normal is that it means every element, so it's closed under conjugates. So you have all of the conjugates. If you have an algebraic element, then you have all of its conjugates as well. So the conjugates of cube root of 2 are omega cube root of 2 and omega squared cube root of 2. But these elements are not in this field, so it's not a normal extension.
Okay, so that makes, like, I makes that as a separate definition, that makes sense to me.
Mm-hmm.
But I don't necessarily see why that definition about conjugates is the same as this definition. Does that make sense? Why? Because like this seems to be about some collection, like some arbitrary collection of polynomials, or like any collection of polynomials, whereas that's a particular one, right?
Yeah. So like Q adjoin square root of 2, square root of 3, square root of 5, square root of 7, ... If you have all of these, like that's also going to be normal because it's a splitting field of a collection of polynomials, like x squared minus p. Right?
Okay.
So like you have this collection of polynomials, and this is the splitting field for that collection of polynomials. So this is a normal extension. And the conjugates of square root of p are plus minus square root of p. Right? And these are all in the field already.
Okay. I'm not sure I understand, but if someone else has a question, something to talk about, I think.
Yes. Oh, does anyone? in the chat. Can we look again why the degree of the extension is the degree of the minimal polynomial? Sure. All right. So you have. All right. Where did I write this? I think it was here. Right. So the degree of the extension. So you have an algebraic extension, and then no, you have an algebraic element alpha. Alpha is algebraic over f, and then the degree of f of alpha over f is the degree of the minimal polynomial. Right. So f is isomorphic. F of alpha, f adjoint alpha is isomorphic to this quotient ring. So you have this ring of polynomials f, coefficients in f, polynomials in x, coefficients in f, mod this maximal ideal. That's this irreducible polynomial. It's the minimal polynomial. And then this tells you that the degree of this extension is is the degree of the minimal polynomial. So first of all, you have that 1 alpha alpha squared dot 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 alpha to the n minus 1 is a basis for f alpha over f. And then you have here n elements, right? All right. Let's say that this was not a basis, right? Suppose it's not a basis. So that would mean that there exists a linear relation, right? B naught plus B1 alpha plus B2 alpha squared plus dot 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 plus Bn minus 1 alpha to the n equals 0, with coefficients not all 0, right? But then alpha is a root of this polynomial, and this has degree less than n, right? But the minimal polynomial had degree n, right? So the only algebraic relations that alpha can satisfy have to be of degree at least n, right? So the smallest algebraic relation that alpha satisfies is degree n. Right, so you can't have an algebraic relation that alpha satisfies of degree smaller than n. So that gives you the linear independence of this thing. And then, yeah, you also show that it's spanning, because if you take any element in f adjoint alpha, right, this is just gonna be linear combinations of powers of alpha, right? Alpha to the m. But then if you have powers that are bigger than n, right? M is bigger than n, or bigger than or equal to n, then you can rewrite those bigger powers, alpha to the m, in terms of the smaller powers, right? You already know. All right. Let me make this a little bit more concrete. Right, let's say the minimal polynomial m alpha of x is this polynomial. I don't know, c naught plus c1 alpha plus c2 alpha squared plus dot 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 cn minus 1, or no, c. So the minimal polynomial is degree n. So we're going all the way up to n. Alpha. Okay. Why did I put alphas? These are supposed to be x's because this is a polynomial, right? So c1x, c2x, cnx, right? So this is, say this is the minimal polynomial. So that means m alpha of alpha is equal to 0, right? So alpha is a root of the minimal polynomial, and what this gives you is a relationship. You can write alpha to the n in terms of the smaller degree guys, right? Minus c naught minus c1x, or minus c1 alpha minus c2 alpha squared minus dot 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 minus Cn minus 1 alpha to the n minus 1. So what we did, we took this we took this nth power of alpha and wrote it in terms of the smaller powers, right? So that tells you how it's a spanning set as well. That tells you how this guy is spanning, right? Because f adjoin alpha, all of the terms in here are just linear combinations of powers of alpha with the coefficients in beta, and then you can write the higher degree terms in terms of the lower degree terms by using the relation afforded to you by the minimal polynomial. Does that make sense? Okay. And then someone asks, so going with this example, if you adjoined omega to q adjoin 2 to the 1/3, would this resulting field be normal because it's a splitting field of x cubed minus 2? Yes. And that's exactly this example. The final example over here, that's a special case of this one, right? So first you have q adjoin the 3rd root of 2, and here you have q adjoin zeta 3, a primitive 3rd root of 3. So this is the case where p equals 3, right? That specializes to what you were saying. First you adjoin this guy, the 3rd root of 2. That's not the splitting field, because we know that the splitting field is this, right? So what you do, first you join the 3rd root of 2, and then you join the primitive p 3rd root of unity, and then you arrive at the splitting field. So this guy is the composite of this field and that field. Right? Composite means, right, it's the smallest field containing both. So first you join that root, and then you join that root. Right. Okay. Cool. All right, so that's it for today. I'll see you on Friday for the rest of this section. Right.